So for those of you who don't know me, I'm Silvia Agnelli, and I have the pleasure to share this lecture with other two experts of rubber, Claudia Marano and Bernd. I carry out my research at the University of Brescia, and I'm focused on the mechanical characterization of soft materials like rubber to boost their development in engineering applications.
Okay, I'm Claudia Marano, and I work in the Polymer Engineering Laboratory of Politecnico di Milano, where my research activity since the last few years has been focused on the study of structure property correlation in rubber compounds, mainly in relation to their fracture behavior.
And I hope Bernd is connected.
Yes, she told me that he has some problem with connection because he entered and then he goes out. So we can start, Silvia, and then
we can start, and he will. I hope he will join later.
Yes.
Okay. So first of all, let me give you some basic knowledge about rubber. Maybe you associate rubber to tires, but rubber is used also for many other technical parts like seals, damper, and hoses. It is important to study fracture behavior of rubber because the failure of these sometimes very small parts can cause large damages, like the explosion of hoses carrying gas. But what is rubber? Rubber is a composite material. It's made by a polymer with special properties called elastomer. An elastomer can be stretched at least up to 100% and can recover all deformation. Its glass transition temperature is below room temperature, and in rubber it is slightly cross-linked. Rubber is a composite made of elastomer and many other additives. A large volume of rubber is occupied by these additives, and the main two are reinforcing filler and vulcanizing agents. Nearly 30% of the volume is occupied by such fillers, and the most important one and common one is carbon black. Carbon black is a black powder made of carbon in the form of spheres or branched particles, and it has a high surface area. Its presence modifies the parameter of the elastomer depending on the amount of the used carbon black. Usually the amount of filler is measured by PHR, which means parts in weight per 100 parts of rubber. The introduction of carbon black, just a moment. Okay, now it's moving. The introduction of carbon black into rubber allows to increase not only stiffness, but also ultimate properties like the strength. This is not common in plastics. This happens because the filler is able to modify the properties of the matrix. Close to the surface filler, in fact, the mobility of the elastomer chains is restricted by the presence of the hard filler. Now let's give a closer look to the mechanical behavior of rubber. Here you can find a sketch of a typical stress-strain curve of rubber, obtained in a tensile test. At the beginning, you can find a non-linear elastic region where stiffness is decreasing by increasing strain. And this is due to several reasons. The first one is well explained by the theory of rubber elasticity. In one of the simplest models, the stress is related to the stretch ratio by this equation, where G is the shear modulus, is the shear elastic modulus. A more convenient way to plot this equation is to use the Mooney-Rivlin plot. When the material follows this model, then the reduced stress is constant with the strain. However, the nonlinearity can be further increased by softening, for example, which is due to entanglement slippage or viscoelastic relaxation. The second main source of nonlinearity is called the pain effect and is due to interaction between filler particles or filler and polymer. These interactions are weak and are lost during stretching, but they can recover when the stretch is removed. In the last part of the stress strain curve, we have that stress increases faster and faster. This is called hardening and is due to chain orientation. Actually, the rubber behavior is a bit more complex than this. If during the tensile test I download the sample, I record the curve which is lower than the loading curve. This creates an hysteresis cycle. This means that rubber can recover its deformation, but dissipates energy. This is due to internal friction due to viscoelasticity, reversible breaks of bonds, and on the practical side, this causes heating. Now that you have some basics about rubber, I want to introduce you how to characterize the fracture behavior of rubber. First of all, let me say that although rubber is an elastic material, it cannot be characterized via linear elastic fracture mechanics methods. Why? Because LEFM requires that nonlinear processes have to be limited to a small size. But in rubber, we have a huge blunting at the notch tip during fracture. You can see the tip radius here called rho star. If we neglect the dissipation effects, we are in this second case, and we can apply, therefore, nonlinear elastic fracture mechanics approaches. In order to determine rubber fracture resistance, historically were developed approaches based on the energy balance, which allow to circumvent the difficulty of finite strains and nonlinearity. These approaches aim at measuring the energy release rate, which is the energy spent per unit of new fracture surface. The working hypothesis is that dissipation is limited to a very small region at the notch tip. If this is not the case, then the material response cannot be separated from the structural response. Historically, two parameters were independently developed, the tearing energy on one side and the J integral on the other side. But until the hypothesis of limited dissipation is fulfilled, these two parameters give the same result. Now I want to give you a very short overview of how to practically calculate the energy release rate in rubber. Commonly, the most used samples are the two represented here. On the left side, we have the pure shear specimen. As you can see, it's very large, quite short. The advantage is that the energy release rate is not depending on the notch length, but you need the special clamps to avoid the slippage because the forces here are getting very high. On the other side, we have a single edge notch intention specimen, which is quite narrow, very high. It's easier to clamp with common jigs, but the calculation is a bit more complex because you have to calibrate the geometry factor exactly for your dimensions. Practically, you need to test a sample with a common test machine and record the load displacement curve. Then you need to identify the onset of fracture on this curve. How? Usually in rubber we use optical methods. You look at the notch tip from the frontal view, as in these pictures, or from the lateral view. In this case, these are pictures that I shoot in my laboratory. We cover the sample with a white powder to contrast with the black rubber. When you start seeing a small black line, it means that the new fracture surface is being formed, and you can identify in this way the fracture initiation point. At this point, we will evaluate the critical parameters. How to calculate them? In the case of pure shear specimen, once that the dimensions requirements are fulfilled, you need to test and notch the sample. Record the load displacement curve, find the critical point, and parallel to this, test also an unnotched sample. On this sample, at the same critical displacement, you can calculate the energy. From the energy under this curve, we calculate the strain energy density. This strain energy density is used to calculate the tearing energy, which is the strain energy density times the height, the initial height of the sample. Alternatively to this, you can use the J-integral parameter. You have to test only the notched sample, and directly from the energy under this curve, you can calculate the J-integral parameter. For single edge notch intention samples, the procedure is similar. You test the sample, you record the load displacement curve, and with these two equations I reported here, you can calculate either the tearing energy or the J-integral. For tearing energy, you need the geometry factor, which is reported in the literature, and this depends on the stretch ratio. And but you also have to calculate this critical strain energy density. With the J-integral, you can use directly the energy under the curve, but you have to calibrate this eta, this geometry factor. Here I reported some results, real results obtained in my laboratory in a work in cooperation with the PCCL, the group of Bernd. Here we wanted to test, to verify the effect of geometry dimensions on single-edge notched intention specimens. You can see that provided that the height of the sample is much higher than the width, we have no effect of the width. The main effect is provided by the notch length. When it's too short or too long, we think that border effects are coming into play. Now I leave the presentation to Claudia.
Thank you, Silvia.
Sharing. Okay.
Sorry, I don't find. Sorry, I'm some problem finding. Can you see my screen? Yes?
Yes.
Okay, thank you. Thank you, Silvia. Okay, in this part of the lesson, actually, at first I would like to report some fracture toughness measurements that were evaluated for several rubber compounds that actually presented a peculiar, non-usual fracture phenomenology. And so I would like to start describing this fracture phenomenology and to saying when it can take place and how it affects fracture toughness. When you load in mode 1 a notch specimen, what you expect is the propagation of the so-called forward crack, which propagate parallel to the initial notch plane. And that for rubber compounds, this occurs after the significant blunting of the tip of the notch, as Silvia has just said. But in some cases, you can observe a different phenomenology. The onset of two cracks then propagate parallel to the loading direction, so-called sideways cracks, can occur before the onset and the propagation of a forward crack. This picture taken at the forward crack onset highlights these two sideways cracks. And why sideways cracks form? It was demonstrated by firm analysis that the tip of a crack in a notched loaded subspaceman, there is both energy available for the propagation of the crack in the forward direction, but there is also some energy available for propagation of the crack in a sideways direction, parallel to the loading direction. But the latter term is significantly lower than the former one. So if sideways crack forms, it means that there is some strength anisotropy at the tip of the crack. That is that the material resistance for the propagation of the crack in the sideways direction has to be significantly lower than the material resistance for the propagation of the crack in the forward direction. Why there is a strength anisotropy in a rubber compound? Rubber, as Silvia said, is a material that is above its glass transition temperature, so the molecules are characterized by high mobility. So there is a significant molecular orientation induced by strain that gives rise to anisotropy in the structure of the material that can be even strengthened if crystallization can occur under strain. And crystallization can take place in some rubbers, not all in all rubbers, in stereoregular rubbers like natural rubber, polyisoprene rubber, and so on. So this strain-induced anisotropy gives rise to strength anisotropy because it's easier for a crack to propagate in the loading direction between the oriented molecules, breaking the weak interaction existing between the molecules, rather than propagating across the oriented molecules, breaking the strong covalent bonds. So strength anisotropy gives rise to the formation of sideways cracks. And even though sideways cracks form, J integral can be evaluated at fracture onset, at forward crack onset, and can still be considered as an index of fracture toughness that, generally speaking, depends on different parameters like the one here reported that all affect the capability of the material to orient under strain, the capability to crystallize under strain, and the capability to dissipate energy under strain. And as I promised you before, here I reported the fracture toughness measured for different rubber compounds. The tests were performed in tensile conditions on a notched pure shear specimen. And the different compounds differ in the type of rubber, natural rubber or synthetic rubber, polybutadiene rubber, a blend of the two, or differ in the filler content or the type of filler, carbon black, silica, and so on. And we can see that in some cases the toughness is relatively low, and in other cases it's high and significantly higher, for example, in these cases. And it was observed that in the cases in which the fracture occurred only through the propagation of the forward crack only, fracture toughness is always low. While in the cases in which sideways cracks formed, fracture toughness reaches very high values. There is no enough time to go into details of this topic, but from all the experiments performed on these compounds that are made with rubbers that are stereoregular, so they can crystallize under strain, we derived a quite general scheme that is summarized, that we can say that with this material, fracture toughness is high when at the tip of the crack, the orientation of the material is enough to give right deformation of sideways cracks, and there is a possibility of the material to crystallize at the tip of the crack that allows to have a strengthening of the material at the crack tip. When this occurs at the tip of the crack, high deformation can be reached in the wall specimen, and so also close to the tip of the crack, and there is a significant energy dissipation that increases the fracture toughness. If you are interested in the study of orientation induced sideways cracks formation, you can perform a biaxial tensile test using a centered notched specimen like the squared one here reported, and you can evaluate how the orientation induced by a preliminary pre-stretched induced by the stretching in the X direction parallel to the notch plane affect the final material toughness measured when successively loading the material in the Y direction. Having no time to report the results on this test, but you can find these results in these two papers. where the test reported were performed using this homemade biaxial testing machine. So I conclude my part and I leave the word to Bernd for his presentation.
Thank you very much, Claudia.
Okay.
Did you see my screen?
Yes.
Perfect. Good. Then, sorry to be late. I will just focus on the presentation now. So at the last slide, I will talk a little bit about the fatigue testing of rubber. And here, basically, we can divide, or basically, the fatigue general is the weakening of material caused by repeatedly applied loads, which means we have a cyclic loading. And when we talk about cyclic loading, then we have two different approaches which we can follow. First is the crack nucleation approach, where we have some sample specimens and we produce curves like where the stress amplitude is depending on the number of cycles to failure, and we have these nice ruler lines. And the second approach is a crack growth approach, where we have a pre-existing crack in the material, which is notched before the test, and then we are producing these Paris plots, where we have the crack growth rate depending on the tearing energy. And here in this presentation, I will focus a little bit more on this Paris plot. And as you see, when you put in here logarithmic and double logarithmic scale, so the crack growth rate over the tearing energy, you have nearly a line, which is called the Paris law. And you see it here, this exponential law, where the slope is m and the intercept is the logarithmic of c. Talking a little bit more about the tearing energy, first of all, I have to mention that the calculation and also the calculation of this tearing energy is depending on the specimen geometry. And so we have here this very easy equation where we have this elastically stored energy per unit volume. Then we have the area under the load displacement. We have the height of the undeformed specimen, and then we have the anchoring specimen area. Then we also have to consider for our tests and also for material performance this load ratio. And this load ratio is more or less the minimum stress divided by the maximum stress. And if this load ratio is bigger than 0, then we have to use this equation for the calculation of the area under load displacement. If it's below 0, then we have to use another equation to calculate this area under load displacement. And when we are talking now about this whole strain energy and also about these different terms of energies, then we can see here that the total energy is more or less divided in two parts. So it's this U and a U min. When we focus here on this hysteresis, on this load displacement curve, we will see here the area directly of the hysteresis as the dissipated energy. Below, we have the stored energy, and then we also have this minimum energy. So there are different ways to define these different energies. We decided to finally move with a minimum energy with F min times S min, because we also want to consider the static load of the specimen. And I will come back to this later, what's the reason behind this. And then finally, we need also the uncracked area, which means the resistant area. Here is the crack growing in the specimen. And then we have residual or the resistant area, which is decreasing when the crack is developing or growing. Effect of testing parameters. As we are doing these tests, we have a lot of different influencing parameters and a lot of different influencing effects. The first influencing effect is for sure the crack growth, and this is also a very critically influencing effect. Therefore, it needs a camera system to directly record the crack growth in the material and in the specimen, because otherwise you cannot really distinguish between X and Y, and it makes difference then finally to calculate your different energies. Moreover, we have a strong influence of the frequency, and this is the first very interesting effect. because when you think of a frequency effect, then it's a little bit special here for elastomers, because when you increase the frequency, the crack growth rate is decreasing. In the first point, we thought it is other way around, but when we screened a little bit the literature and we also thought a little bit of it, then we found also different papers which are explaining this, where you have different contributions to your crack growth rate, which means that you have a static contribution and a dynamic contribution. This means the static contribution, as you see it here, has the strong impact of the frequency. And when the frequency gets lower, this static part getting higher. And as you increase the frequency, the static part is decreasing and the dynamic part is overtaking. And therefore you have a lower crack growth rate by comparable tearing energies. The next effect, what we have found is that when we go to zero or even below zero, which means that we go to tension compression of our material, also the crack growth rate is increasing a little bit at comparable tearing energies. And finally, a very important effect is the temperature effect. You see here also that when we increase the temperature, also that the crack growth rate strongly increases at comparable tearing energies. And on the next slide, we will talk a little bit more about the temperature effect, because we have now this IR camera and we are directly monitored the temperature during the fatigue tests. And what you can see is that with an increasing frequency, you have a clear increase of your temperature during your fatigue test. And what you see here on the right side are two pictures where the temperature profile directly in front of your crack tip is developing during the test. And what you also can see here, this is the crack tip, and also this temperature field in front of your crack tip is getting undeformed by this growing crack tip into the material. And what I also have to mention here is that this is always the surface temperature we're talking, which means that in the material the temperature is even higher. To get a little bit closer and to discuss different materials and also the temperature effect a little bit closer, we have developed or we have implemented tests with two different materials. As you can see it here with material A and material B, the both are rubber compounds, but the first one, material A, shows a nearly linear behavior, whereas material B shows a strong non-linear material behavior, where we have a much higher deformation during the loading. This is also directly reflected in the surface temperature, what you can see here, where you have material A, 31, and at 4 Hertz, 49, whereas for material B, you have even with 1 Hertz, 45 degrees, and with 4 Hertz, sorry for the mistake here, it's 4 Hertz, you have even 94 degrees. And this exactly brings you in a region where most of the rubbers are really affected by the temperature, and you're going to thermal degradate, or where you go in the direction that your material starts thermal degradation during your test, and you do not do any more fracture mechanics because you're just destroying your material. And then, one more time, we're talking here about surface temperature. We went also one step further, where we used some sample specimens only to show the temperature impact, where we directly molded the thermocouple inside of the sample specimen, where we've seen here an even higher temperature increase compared to this surface temperature, what you can see here. So from my side, thank you very much for the attention.